This is lecture 11 for Logika or računalništvu, and in today's lecture and also the next lecture we're going to cover a new topic, which is program verification and a particular style of verification using a dedicated logic that's designed specifically for program verification called Hoare logic. So to set the scene for what we're going to do, I'm going to remind you of the one of the main goals in the course, right from lecture 1. So a main goal of this course was to look at technology that various kinds of technologies that we have for showing relations of the kind so it was to consider how to establish, if you like, relations of the form which I was writing, I think, in the first lecture like this. S models phi, where this was a system satisfies property. And as I said, this is important in a number of different guises. That's different forms in computer science for different kinds of systems and different kinds of properties. So in the last few lectures, we looked at LTL and LTL model checking, and that indeed provided exactly what we wanted, a technology for establishing these kind of relations. So LTL model checking provided this explicitly. And in that case, we had that for LTL model checking, the systems S is so the system S was a finite state transition system. Finite state transition system. And phi, a temporal property. That's a formula of LTL. So phi, a temporal property about time in LTL. And the important thing, the other important thing in this case, what we spent quite a lot of effort on in the last 2 lectures, is that this model checking verification, so actually checking whether or not this relation holds, is automatic, it's algorithmic. So moreover, model checking is automatic. There are nice algorithms to establish whether or not the property holds. So, as I've already described to you, LTL model checking is appropriate when you have properties that you can talk about in temporal logic, and where you have systems that can be modeled using transition systems. And as I mentioned at the start of the last block of lectures, so that would have been lecture 7, transition systems are particularly good for modelling concurrent systems. concurrent systems, that's parallel systems, where there is a lot of non-determinism. One of the important things was we have many potential execution paths. We don't know which one's going to be followed, so we establish properties that hold for all execution paths. So today what we're going to do is switch completely to a totally different modelling paradigm for systems. So we're going to change our computational paradigm from transition systems, which are modelling concurrent systems, to something completely different, but actually rather familiar, hopefully, to almost everyone. So we're going to switch to a completely different so the paradigm is kind of the basic setting we're considering for what a system is. And this paradigm, let's write it in red because it's important to highlight this. This is going to be sequential imperative programs. So sequential as opposed to concurrent. So that is commands are executed in sequence. Atomic actions of the program are executed in sequence. And imperative meaning that the program, as it computes, acts on the state of the computer by changing the memory. In the case we're going to look at. So the standard model of a program where you have a computer has its internal state of its memory, and the program uses the current state of the memory to do something, and then potentially changes the memory as it computes. So sequential imperative programs. And here's an example, a very simple example, and this is also, for some of you who've covered this kind of material before, this is the example that's almost always used, and but it is a good example, so I'm going to use it as well for the same reason that everybody else does. So just to illustrate the kind of programs we've got, we're going to allow, we're going to have memory, and we're going to have identifiers or variables or locations or whatever you want to call them. Different programming languages have different conventions for this. So this is saying, so we have assignment statements that say we can assign a value to a variable, and we view this as the location in memory addressed by y is assigned the value 0. And different variables will refer to different locations in this language. So z is a different variable. We assign z to 1. And then we're going to have loops. In particular, we're going to have the while loop. Doppler. So while, and here's the condition. In many languages, one would put this in round brackets, but I'm not going to bother to do this. While y is less than or equal to x, do, and then I'm going to use indentation for scoping, a bit like in Python. For those of you who know Python, well, almost everyone does, because you all wrote sat solvers in Python, mostly. Okay. So set y to 0, set z to 1, and while y is different from x, which we haven't set to anything, so we think of x as an input value, somebody sets the value of x, then we run our program. I mean, if we wanted to include an input command, we would put input x here. Anyway, we're given the value of x, we check to see if y is different from x. If it is, we increment y and multiply z by y. Z's a kind of accumulator here, accumulating the result as we go along. And as many of you can see, this is a factorial program, so I'll call this program, so this is the name for the program, pfact for the factorial program. So that's it. We call this program, I'll just so that anyone looking at the notes knows what's going on. Let's write it a bit more neatly. We call this program pfact. And if we wanted to state the correctness of the program, then, well, let's do it informally first, and in the end we're going to do it formally using Hoare logic, which is the logic we're going to introduce for exactly this purpose, for being able to state and prove the correctness of the program. That's it. Informally, before we look at the logic, the correctness of the program pfact. By what I mean by correctness is that it's a correct program for factorial, in this case, is expressed by the combination of two properties. So by the following two properties in combination. So we could express it in one property, but there's a reason that I'm going to separate them, as you will see later. So I could wrap everything up in one, but I'm not going to. So the first point is that if our program pfact starts execution in a state in which x is greater than or equal to 0, and if its execution terminates, so and if the execution of the program terminates, then it terminates in the state in which, well, the point is, if we look back at the program, that z is calculating the factorial of x. So when we the value of x here doesn't change. So when we terminate the value, that means when we exit from the while loop, because there's nothing else beyond the end of the while loop. When we exit from the while loop, the value of the variable z will be x factorial. So we terminate in a state in which z is x factorial, using the exclamation mark for factorial. Just maybe, for those of you not familiar with the English language here, so just remind you n factorial is defined to be 1 times 2 times all the way up to n. And the second property is that actually if pfact starts execution, again, in a state in which x is greater than or equal to 0, then execution does indeed terminate. So whatever value, as long as x is greater than or equal to 0, well, if it's 0, we terminate immediately because we don't even go into the while loop. If it's greater than 0, well, the value of y eventually counts up as every time we go around the loop. And I should have said more explicitly, perhaps I'm only considering integer variables here. So we've got integer variables and y counts up, and if x is strictly greater than 0, eventually y will get to the value of x. So it terminates. So as I mentioned already, we could have wrapped statements 1 and 2 into a single statement in which we say if pfact starts execution in a state in which x is greater than or equal to 0, then execution terminates, and it terminates in a state in which z is x prime. But I want to separate these two out because this property, the first property, is of interest in its own right, and so it has a name. So here the point is of this first property is that we're establishing a correctness property that does not include termination as part of correctness, but then if we can separately prove termination, then we've also got a separate the full correctness property that involves termination. So because of this is like a sort of partial statement of the full correctness of the program. This is called partial correctness. Property 1. And property 2 is called termination. And Hoare logic is going to give us a way of, in the first place, for today's lecture, stating partial correctness properties. Next week, we're going to also look at proving termination. This week, we consider Hoare logic for partial correctness. Statements like one above. Oops, it's a bit messy. Like one above. And in Hoare logic notation, property 1 is written. So what this is saying, this property that if pfact starts execution in a state in which x is greater than or equal to 0, and if execution terminates, then it terminates in a state in which z is x factorial. This is written in the following way. We write here in curly brackets a condition, which is the property we assume holds before execution starts. So that was that x is greater than or equal to 0. Then we write the program that we're verifying. And then we write the property that we want to establish that holds if execution terminates. So in our case, this was that z equals x factorial. And in general, this is just an example of what's called a Hoare triple, expressing the correctness property of a program. A triple because it consists of 3 programs. The left-hand side here, which is the condition we assume holds before we start executing the program. It's called the precondition because it's pre-execution, that's before execution. The second component is the program itself. And then we have the condition that we want to hold after execution. That's called the post condition because it's a condition for post execution, that's after execution. So this is an example of a Hoare triple, and the general form for such things so this is specifically for p factorial, but in general for arbitrary programs p, or rather imperative programs p, we specify behavior. So we want to specify the conditions we want the program to satisfy. So we can call that specify program behavior. Using, as I've said, what are called Hoare triples. So this is of the form we have some logical property phi, which is the condition we want to hold before we execute the program. We assume holds before we execute the program p itself, and then the condition that we want to hold after the program executes. So this is as I said, precondition. Program post. Oh, that's right. That's a bit more neatly. This is going to say post condition. Right. So we have statements of this form. And we're actually going to consider this week and next week 2 ways of interpreting Hoare triples. So the first one is partial correctness, which we've already talked about. And what this says And what this says in general is, so for this particular program triple, Hoare triple here, is this says if P starts execution in a state satisfying phi, and if execution terminates, then it terminates in a state satisfying psi. So again, the key idea of partial correctness is that we don't need to prove that the program terminates, we only establish correctness if the program terminates. Then it terminates in a state satisfying psi. And the second way is total correctness. And that is a stronger property where we actually establish termination as part of the property. So this is if P starts execution in a state satisfying phi, then it terminates. It really does terminate and it terminates in a state satisfying psi, satisfying the post condition. So we see then that total correctness is the same thing as partial correctness plus termination. So it's a stronger property than partial correctness. So today we're going to focus on partial correctness. Next week, total correctness. Next week, total correctness. Okay. So what I want to do now is essentially introduce, and I'm just going to repair that O because it's a bit messy. Still messy, but never mind. So what I want to do now is essentially introduce the Hoare logic proof system for establishing total correctness, and we're going to do that by verifying the factorial program. Uh, but let's begin by looking in general at the programming language we're going to, or actually, maybe I'll verify the factorial program and then after that we'll look at the generalities. Yeah, so let's do that. So we're going to proceed to the verification of the factorial program. So we want to, maybe let's go to a different sheet of paper. Well, not really paper, but anyway, a different sheet. So I think it's good to start with an example rather than going immediately into the generalities. So let's look again at pfact and what we want to verify. Well, here's what we want to verify. So we verify so what I said we wanted to verify was this, which is that if x is greater than or equal to 0, then pfact, we follow that by pfact, then at the end of it, z is x factorial. But because we're interested in partial correctness, we actually don't need the precondition that x is greater than or equal to 0 here. Because if x is greater than or equal to 0, go back to the program, if x is greater than or equal to 0, this program will execute and it will terminate, and indeed at the end of the termination, z will be x factorial. We want to see how we can prove that. But if x is less than 0, then we're just going to go into an infinite loop. So it will never terminate. So in fact, because the partial correctness assumption does not require establishing termination, we only need to show that z equals x factorial holds if the program terminates. In the case that if we start with a negative x, well, the program will not terminate, so this statement will be, this partial correctness statement will be vacuously true because the assumption of termination just won't hold. So in fact, what we're going to establish is a stronger property. We don't make any assumption on the precondition. So this is here the empty precondition. Which we view as being true because it's basically in general, we're going to write a list of formulas in here and we consider it as the conjunction of all the formulas. And this is like the empty conjunction, so it's true. So under no assumptions, that's under true. If we execute pfact and if it terminates, then z will be the factorial of x. Because it will if it terminates, actually x will have been greater than or equal to 0. Right, so to verify this, well, I'm going to give you the whole proof a little bit later, but I want to talk through the interesting parts. So, of course, the most interesting thing in the program, go back to the program, we've got a couple of assignment statements, but the most interesting thing is the while loop. So while y is not equal to x, do y becomes equal to y plus 1, z becomes equal to z times y. So the loop is where the interesting computation happens. So But the interesting part of the verification is verification of the while loop which I'll call W. So the while loop was while let me remind myself, while y is not equal to x, do y becomes equal to y plus 1, z becomes equal to z times y. Maybe put these in brackets just to emphasize that this is all inside the body of the do loop. So how do we verify a while loop? So we want to establish, so basically the idea is we're going to break down the program into its parts and verify appropriate Hoare triples for its parts. And as we get to simpler parts, then the verification becomes simpler. It is called compositional verification. We verify a complicated program by verifying the parts. One part of the program here is the while loop. The main part of the factorial program is the while loop, so we want to verify that. And we're going to so for this, we use the while proof rule. Whoops, so the while proof rule says that if we want to establish, in general, if we've got a while loop, so a while loop is always of the form while some Boolean expression here, which is the test, do some code that we execute while the test is true. And we call such thing commands. So here the command is y. So here the Boolean test is that y is different from x, and here the command is that y gets assigned to y plus 1. That gets assigned to y increments, and then z gets multiplied by y. So that's the C part here. But there's the general rule we use for verifying a Hoare triple of a while loop is the following. So suppose that we want to verify a property of a while loop. Well, how can we do that? Well, the complicated thing about a while loop is we don't know how many times the body here of the while loop will execute, because that depends on the value of the Boolean test. So it's difficult to know how many times this is going to be executed. So the main thing we can do with a while loop, the important thing to do, is establish what's called an invariant of the while loop, which I'm going to use eta for the invariant. And the point of an invariant is that it's a property that essentially, if it holds before we execute the body of the while loop, it will hold again after we execute the body of the while loop. Then if we assume that the invariant holds before the while loop, then however many times we go round the body, if we go none, then we haven't done anything, so the property still holds. But because the invariant means it doesn't change, and the point is it's preserved, the property stays unchanged by the body of the while loop. However many times we go around the while loop, if we terminate, if we come out, which is where partial correctness comes in, then that property will still hold. So the point is, if we've got such an invariant property, eta. My Greek letters are not very neat, but anyway. Then we can establish, that eta holds. So if we've got an invariant property and it holds before the while loop, then we can establish it holds at the end of the while loop. And the invariant property then, to show it's invariant, we need to show that if we have the invariant property and C holds, and we run C, then and C terminates, then we still get back the invariant property. So this would be a correct proof rule for while B do C, with the justification basically as I've described it. But actually we can establish a slightly more useful version of this, which is the rule we really need, because there are two ways we can adapt this rule. So the first property is, the first modification is that, so suppose the invariant property holds before we go into the while loop, then we go into the while loop, well, we will only go into the body in the case that this Boolean test is true. Because if the Boolean test is false, we don't go into the body of the while loop at all. So we don't actually need to show that C preserves the invariant property always. C only needs to preserve the property under the further condition. So if the more conditions we add, they're all conjoined together. They're joined by ands. So under the further condition that we only need C to preserve the property eta, the invariant property eta, under the condition that the Boolean test is true, because we will only start executing C if that property is true at the time that we start executing. Once we've executed C, B might no longer be true, so we don't want to put it this side. Indeed, in order to ever exit the while loop, we rely on eventually B becoming false, because when our Boolean test becomes false at that point, we execute the while loop. But when we execute the while loop, so that's when we come out of the while loop at the end, we have the post condition, so our invariant property will indeed hold at the post condition, but because we exit the while loop when the test property becomes false, we can conclude something stronger here, which is that the negation of B is true, so B is false. So this is the while proof rule. So we want to use the while proof rule to establish an appropriate property of the while loop for the factorial program. So let's go to another sheet of paper, and maybe we'll start at the bottom. So actually, let's write it out in full. I was going to just write W, but let's actually write it out in full. So while y is not equal to x, do y is incremented and z is multiplied by y. So we want to find an invariant property that's going to be true when we start executing this loop and is preserved by the loop itself. Well, if we go back to the context of our program, because we're going to be verifying the while loop in the context of the larger program, when we start the loop, we've set y equals 0 and z equals 1. When we start the loop, it's already the case that z is x factorial, but when we start the loop, it's the case that z is y factorial, because 1 is 0 factorial. And if we go through the loop and z is y factorial, so z is 1 times 2 at the so if we enter the body of the loop and we've got that z is y factorial, so z is 1 times 2 times 3 times 4 all the way up to y. Then we add 1 to y and multiply z by the new y. Then we've got that the new z is still, well, is 1 times 2 times 3 times all the way up to y plus 1 of the original y, which is now 1 times 2 times 3 all the way up to y of the new y. So the point I'm trying to make is that if y is if z is y factorial before this code is executed, then z is still y factorial after these 2 lines of code are executed. So our invariant property is going to be that z is y factorial. And also, just to make sense of that, we'll assume that y is greater than or equal to 0. These are integer variables. So this is our property eta. And we're then going to want to show, so then our while rule will establish, once we've done this, that the invariant property still holds. And moreover, the Boolean test is false. So that means then you get that y is not equal to x is false. So at the end we get that y equals x. So this is the property we're going to prove of the while loop in Hoare logic. And our proof rule here says that we can do this if we can prove that as long as the invariant property holds together with the test before we execute C, then the invariant property still holds. So here we get that if z is y factorial and y is greater than or equal to 0, and now we can assume that the test property does hold and y is not equal to x, then if we execute the body of the while loop, then the invariant property still holds. Okay, so to establish this, we need to now have a rule for the sequencing operation semicolon here, because this program here is now a sequencing of 2 assignment statements. So we're also going to use the sequencing rule. And the sequencing says that I'm just trying to find it in my notes, so I use the same notation. So the sequencing proof rule that says if we're trying to establish a Hoare triple where we've got a sequence of 2 commands, then to do this we want to again break it down into simpler goals. Now, this time concerning the command C1 and the call and the command C2. So here we want to say if phi holds before we execute C1, then C2, then psi holds at the end of it. So to break that down, we find an intermediate property, eta, let's say. So we find some property eta such that we can establish that if we execute C1 in a state in which phi holds, then eta holds, and then because after executing C1 we go on to execute C2, then if we execute C2 in a state in which eta holds, then psi holds. So I need to find an intermediate state eta that will hold at this point. So I can split this into two goals. And let me tell you that an appropriate intermediate goal, so here one needs to be able to see what an appropriate intermediate goal would be, but there are in fact ways of doing that which we'll come to a little bit later. So here an appropriate intermediate goal is that z is y plus 1 factorial, as it turns out. Is that right? Let me just think. So we want to show that z so this command here, z is assigned y times z times y. Sorry, that's copied out right. Sorry, I just mentally froze for a second. So we want z is assigned z times y, and here we have z is y factorial, y greater than equal to 0. And well, actually, let me put the condition in full because I don't see a way of simplifying it quite as I said. So here the correct precondition to put in is z times y equals y factorial, and y is greater than equal to 0. And this is simply true because of the assignment rule. And I'll talk you through it in a minute. So the assignment rule says that it's an axiom, and it says that if we have an assignment x for any postcondition, then we can prove this for the statement that substitutes. We can prove this from the precondition where psi, where all occurrences of x in psi are instantiated with the expression e that's calculating the numerical value we're assigning to x. So whatever the postcondition, we substitute the value we're assigning to x into the precondition. So let's now look at what we get from that. So here we can establish this assignment. The axiomatically we get that a correct Hoare triple for an assignment statement, we want the postcondition here that z is y factorial and y is greater than or equal to 0. So we substitute for z, we substitute z times y. So here we've got a z, we substitute z times y for it, so we have z times y equals y factorial, and y is greater than or equal to 0. So I was tempted to write z is y minus 1 factorial, but that's not completely correct because if y equals 0, then we obviously, if y equals 0, well, if y equals 0, this thing's never going to be true anyway. But we'll see how we get rid of that problem in a moment. So the point is, if this is true, then this will be true, and this we've just got by substituting z times y here. So it's clear that if this precondition holds here, then because the value of z here is the value of z times y at this point, because we've assigned z that value, then it's clear that because this condition was true with the old value of z, this condition is true with the new value of z. So it's clear that this rule is correct. And then we can do exactly the same thing for the y plus 1 assignment. The point is we want to here use the sequencing rule. So this condition here, which is the precondition for the right-hand assignment, so this eta, which is the precondition for the right-hand assignment, this needs to be the postcondition for the left-hand assignment. So here we want to establish that, so we take our postcondition here, so z times y, maybe I'm going to make my pen a bit thinner, and that'll help. So let's go to, so we're going to have z times y is y factorial, and y is greater than or equal to 0. And we want to show that then if we assign y to y plus 1, then in order to be able to use the sequencing rule to using these two premises, one for y equals y plus 1 and one for z equals z times y, we need to have the precondition of this assignment needs to be the precondition of this triple here. So here we need z equals y factorial, y is greater than or equal to 0, y is not equal to x. So now we've got an assignment statement, but now the left-hand side here is not simply the right-hand side with y plus 1 substituted for y. So we can't conclude this as an instance of the assignment rule. So the question is, does it follow from the assignment rule? So the assignment rule would give us that if z times y for this postcondition and y greater than or equal to 0, if we increment y in the middle, well, this will hold with if we substitute y plus 1 for y. So that's what the assignment rule gives us. So here we have z times y plus 1 equals y plus 1 factorial, and y plus 1 greater than or equal to 0, which is the same as y plus 1 and y plus 1 greater than or equal to 0. So this is an instance now of the assignment rule. So let me just So let me just annotate the rules. So this is assignment, this is sequence, and this is while. So the question is, so we have a completed proof as long as we can justify that this Hoare triple implies this Hoare triple. So here we're saying if this precondition holds, and then we assign, and then y becomes equal to y plus 1, then this postcondition holds. And here we're saying if this precondition holds and y becomes equal to y plus 1, then this holds. This we know. So it's enough to show that if this holds, if this precondition holds, then this precondition holds. So this is so this follows using a rule called the consequence rule, or the I'll call it the implication rule. And so this is justified by let's keep it in blue. This is justified by that if z is y factorial, y is greater than or equal to 0, and y equals x, then all these conditions together imply that z times y plus 1 equals y plus 1 factorial, and y plus 1 is greater than or equal to 0. Okay. So we have verified now this triple using this combination of rules. We still haven't completed the proof of the whole program. Oh, sorry, before doing that, so let's just write so the last one is the implication rule, which is that in order to show any Hoare triple by C psi, it's enough to show some Hoare triple for C with different properties So if we can show that the postcondition, the precondition phi implies the precondition phi prime, is that the notation I used? Yeah. And the precondition psi prime, postcondition psi prime implies the postcondition psi. Notice the arrows go in different directions, but it's completely intuitive because suppose we've established that for precondition phi prime, if precondition phi prime holds and C is executed, then psi prime holds. Now suppose we have these two conditions and suppose phi holds as a precondition, then by this implication phi prime holds, we then execute C, psi prime holds, and by this implication psi holds, and so we've established if phi holds and we execute C, then psi holds. So this is a correct rule, and it's a very important rule in Hoare logic because it allows us to change the property we've got in order to get it into the form that we can use the rules. So in this case, we used the assignment rule to derive this, and then using the implication rule, we massaged it into the form we needed to below use the sequencing rule, and then below that the while rule. Okay, I'm not actually going to complete the proof here because it's getting a bit messy and complicated, and I want instead to go to slides where I actually have the full proof of this written out here. So here is indeed the proof. I'm just using some abbreviations, so W for the while loop. Here's the full proof, only there's another step on the bottom which again uses the implication rule, which let's just add to our proof here. So again, using the implication rule at the bottom, just to give another example of that, and because this is useful in the verification of the whole program. So we have while, and we have all. Then here we can have the simpler condition. So if z is y factorial, y is greater than or equal to 0, and y equals x, then in particular, well, because z is y factorial and y equals x, this implies that z is x factorial. So this is how at the end, so let's put again implies. This is how at the end we get our the conclusion we want for the whole program, that indeed the z is computing the factorial function of x. We go back to the proof, the whole proof in the notes. So here it is written out. So the thing is about these proofs is they're rather complicated. So this is the proof here of the whole triple that we wanted, that assuming nothing, if we execute the p factorial program, then z is x factorial. The right hand, we have the right hand, the left hand branch is because we've got some assignments and then a sequence with w. The right hand branch is basically the proof we've just done in the notes. The thing is, if you have a long, big program like this and you start writing out the proofs as trees, they get very big and very messy very quickly, and you have a lot of duplication. So for example, whenever there's a sequencing, you have the same condition appearing both as a precondition here and a postcondition, and it's rather complicated, and nobody would ever want to do this sort of thing in practice. So fortunately, there's a much nicer way of writing these proofs. So what I want to do is talk you through rather briefly now the proof of the while program in the actual way one really does it. But I wanted to first start in the way of writing the proofs as trees in order to be able to properly introduce the proof rules, which are important to understand in order to understand the soundness and completeness properties of Hoare logic, which we will look at a little bit in this course. So let's make an analogy that when we did natural deduction in the first two parts of the course, both for propositional logic and predicate logic, we were also writing rules as in this form of premises above. Here we've got one premise, here we've got two premises, and conclusion below. But we didn't write our proofs out as trees built using the rules, because that would have been cumbersome. And indeed, this is an example of trees written out using the rules as being cumbersome. So instead, we gave ourselves a nice sequential way of writing the proofs in natural deduction for propositional and predicate logic. So also for Hoare logic, there's a nice sequential way of writing out the proofs. So that's what I'm going to end with for this. That's what I'm going to end with for this half of the lecture. So we're going to write out the Hoare program with plenty of space. So we start off by setting, maybe that's actually, I said plenty of space. Oh, there's actually a lot of space up there. I didn't mean so much space. Oh. I can give myself a slightly thicker line for this, I think. Oh, that's the wrong one. Let's go. Right, so need enough space. We're going to do, let's start here. So first we set y to 0, so we do the initialization, and z is equal to 1. And then we have the while loop. So the while loop is while y is different from x, do, and then we're going to have things we do are we assign, we increment y, and we modify z. And that's the whole program. If I zoom out, you can see the program. And the point of writing it in this, with the space between, is we're going to annotate the program with assertions about the current properties of the state as we execute it. And what we want to do, let's switch to blue to separate the annotations. What we want to do is we want to show that, so we assume to begin with, well, we don't assume anything, we're just going to assume the empty assertion. So this we call, this is the precondition. And at the end, we want to establish that z is x factorial. So this is the postcondition, but we don't write postcondition. What we want to do is we want to give ourselves a chain of properties established through the program that lead us from the precondition to the postcondition. And we're going to apply certain rules, basically the same rules we had before, but with the tableau interpretation. So we're going to call this a tableau proof for the verification of the while program. And we're going to use these same rules, but we can write them in a nicer way using the tableau version of the proof, just as we could use the natural deduction rules in a nicer way if we wrote proofs in a sequence when we did natural deduction for propositional logic and predicate logic. So how we work back from here is, well, what we want to do is we want to establish now the property of the program. So the program consists of 3 commands in sequence. I suppose I should put a semicolon here. So this command, and then the while command. And then the while command has its inner loop. So first we want to establish a property for the while command. And just as before, we find our invariant property. And our invariant property was that, just as before, was that z is y factorial and y is greater than or equal to 0. And the way we write things are, so we write our invariant property for the while loop here. So z is y factorial and y greater than or equal to 0, together with the negation of the test, y equals x. And we write the invariant property here without any other information. So z is y factorial and y is greater than or equal to 0. And the point is, this statement here is the precondition, is immediately before the while block. That's considered its precondition. And this statement here is immediately after the while block. That's considered its postcondition. So here we've basically stated this line here: the precondition, the while block, and the postcondition. So this is the last line of the while rule. And the first line of the while rule says, then in order to prove this, we need to establish a similar thing for the precondition for the inner command of the while loop, the inner block of the while loop, with this as the precondition, the invariant together with the property we're testing, and again just the invariant as the postcondition. So we write these before and after the inner block. So the inner block is these 2 statements here. So here, as its precondition of the precondition of the inner block, we have the invariant property z equals y factorial y greater than or equal to 0, together with the test property, so y not equal to x. And at the end, we're going to have just the invariant. Z is y factorial, y is greater than or equal to 0. So notice this, with these 2 statements followed by this, is stating the premise of the while rule. That's this line here, the line above the while rule. And that's why I'm writing these assertions here, the precondition and postcondition, indented, because they're stating a property of this indented block here. And the non-indented version is the precondition and postcondition of the whole while loop. And the point is that as long as we can prove this part and we can establish this condition here, then this is a justification of this rule. So we say that this, sorry, not this rule, but this statement here. So this statement here is justified by the while loop, by the while rule. I'm going to call it partial while, just because next week we're going to have a total while. So perhaps I should annotate that up here. put it in brackets. So it's partial while because it's partial correctness. So this statement is justified as long as we can justify this, and we don't need to justify this precondition here was given for us. As long as we've justified that this precondition holds before we go into the while loop, then this condition will hold every time we come round and start executing the body in the while loop. So here I call this the do precondition, because this is the precondition of this do block. And the thing is, if we've justified this statement, so whenever I write something on the right, it means it's justified. If we've justified this statement, then because if z is y factorial, y is greater than or equal to 0, and y equals x, that implies that, of course, if y equals x and z is y factorial, that of course implies z is x factorial. So we've also justified this statement. So this statement is implied. And the goal is to get back to the beginning, to the precondition, with every statement justified on the right. So when we split things up for a while loop, when we find an invariant property, we can then justify the conclusion of the while, by partial while, and we justify at the same time the precondition of the do loop, of the do body, so the body of the while loop. So we write do precondition here. We still need to justify this, and we still need to justify this. So to justify that z equals y factorial and y is greater than 0 after an assignment, well, we just do what we did before with the assignment rule. It's enough to then justify that z times y is y factorial and y is greater than or equal to 0. So that justifies this by assignment. As long as we can justify this. And we can justify this by assignment by, well, so if this is to hold after we've incremented y, then before we increment y, we need that z times y plus 1 is y plus 1 factorial, y plus 1 is greater than 0, and that's all. But once again, this is implied by the line above. So sorry, this here we've justified this statement by the assignment rule, assignment. And here we have a statement that follows from the line above, because if z is y factorial and y is greater than or equal to 0, then indeed z times y plus 1 is y plus 1 factorial. And if y is greater than or equal to 0, then of course y plus 1 is greater than or equal to 0. So this is again implied from what's above. So to finish the proof, in this tableau form, we need to now justify this statement that after assigning y to 0 and 0 to y and 1 to z, that z is y factorial and y is greater than or equal to 0. That's absolutely obvious. Y is 0 and 1 is z factorial. But to do that using the rules, well, we again use the assignment rule. So to justify this using the assignment rule, we're assigning 1 to z, so we replace z by 1. So we have 1 is y factorial and y is greater than or equal to 0. Now we have the assignment rule for y, so we need to substitute. We need to substitute 0 for y, so we need that 1 is 0 factorial and that 0 is greater than or equal to 0. And of course, both these statements are true, so they are implied by the empty condition where we're not assuming anything. This was just true. So this is again implied. And now we have a complete annotated code, annotated with a set of statements about the state at the current time that we execute so in between executing the different parts of the program. Everyone is justified on the right because it's been working backwards from the conclusion we wanted. We've managed to work our way to the precondition at the start, which was justified just because it's the assumed precondition. By applying the rules we have for constructing the tableau proof, and everything here is justified. Okay, so let me just go to the slides, and just to say that I'll talk you through this a little bit later, but just to say that the rules for forming tableau rules are going to be explicitly written on slides that will be linked to from the lecture, but I'll talk you more through that in the second half. So I think that's enough for the first half. What we've done is we've verified the factorial program first in the slightly complicated way, first in the way that uses, that's the same proof, but first in the way that uses these trees, that's a bit cumbersome, but second in the nice way using this, what's called the tableau approach to Hoare logic verification. So let's call this as a tableau proof. Okay, so in the second half, we'll look a little bit at the general setting for this, and we'll do one more example much more quickly. Okay, so that's enough for this half.